Okay, now let's get to the business of calculating R. Really, you could think of the correlation coefficient as roughly the average product of the z-scores for x and y. Let's recap a little bit what the z-scores are. So z-scores are just giving you how many standard deviations away you are, right? Like, we don't want to know it in terms of the raw numbers. We want to know it in terms of standard deviation, right? So we don't want to know like how many feet away, but we want to know how many standard deviations away. So you could think of the standard deviations as jumps away from the mean, right? So how many of those jumps away are you? And that's the z-score. So here's how we calculate R, the average product of z-scores for x and y. So let's put the z-scores for x and y and multiply them together because we're getting the product, right? So the product is z of x times z of y. And I'm going to sum them together and then divide by n minus 1. Later on, we'll talk more about why n minus 1 is more frequent. But you could roughly see it's about roughly the average. And mostly it's because we're jumping from samples to populations. We need to make a little bit of correction. But you know, this formula of adding something up and dividing by n is an average, right? And the thing that we're averaging are the product of the two z-scores. Now, for all of these formulas, you could think of these as like these little like z-scores as like almost like you could double click them, right? And if you double click them, sort of what's inside. Well, each z-score, let me write this in blue. So each z-score is really sort of the distance away from the mean, but not the raw distance. I want it in terms of standard deviation jumps away from the mean, right? So that would just be something like my y minus y bar, right? The mean, right? So that distance divided by the standard deviation. And here I'll just use little s, right? And also for z of x, that's just x minus x bar. So that's the raw distance away from the mean, but divided by its standard deviation. So I'll put a little x here to indicate the standard deviation of x's, and I'll put a little y there to indicate the standard deviation of the y's. And I'm going to multiply those together, and I'm going to add them up for every single data point that I have. So if it's my twin data, for every single set of twins that I have, right? And so, and then we want to divide all of that by n minus 1. And n is my number of cases. How many twins have you got, right? How many sets of twins have you got? Now, if we wanted to, although it goes without saying, this does implicitly have an I that goes from 1 all the way to n, because it's for every single one of my data points that I need to do this, right? Now, furthermore, we could sort of double-click, right? Double-click on each of these, on these little standard deviations. Now, how do we find standard deviation? Now, standard deviation is the square root of sort of the average distance away from the mean, right? So the average distance away. So square root of average squared distance, which just gives us average distance away, right? And so S sub y, right? This is, think about the distance, right? So we already know how to do distance because we've already done it, right? And it's average squared distance, right? Because remember, it's sum of squares over n minus 1. Now, remember, it's sum of squared distances because if we just add if we just got the sum of the differences, then we would just get something very close to 0, right? So we don't want that. And we divide by n minus 1 because that sum of squares is very small, so we need to correct for that by going from samples to population, so that's why we divide by n minus 1. And because we want the standard deviation and not the variance, we're going to square root this whole thing, right? Same thing for s sub x. It's the same thing, except you substitute in x's here instead of y's. Oh, I forgot to put my little sigma notation because I want to do this for every single y. Right? So although it looks sort of complicated if we write the whole thing out, right? Like if we wrote the actual like unfurled or double-clicked version of the s sub y in there, it might look sort of crazy. What you do have to remember is ultimately this is the main idea you want to sort of like get out of today. And then you want to take a moment to think, okay, what's z-score, right? And then once you unpack z-score, then take a moment to think, okay, what's standard deviation, right? And hopefully you'll be able to unlock those things as you go. Then you don't have to remember all of that stuff at once. You could just remember them one at a time. All right. All right, now that you know the formula for correlation coefficient, now let's talk about the relationship between correlation and slope. Now, already we know that B1 and R have the same sign. So if B1 is negative, R will be negative. If B1 is positive, R will be positive, right? And vice versa, right? So we already know that they have the same sign. And because of that, they already slant in sort of the correct way, right? But remember, R doesn't have anything about rise and run in it. All it cares about is how much like a line it is, right? And so B1 and R have a very strict relationship, where R, when you multiply it by the standard proportion of standard deviation of y over the standard deviation of x, as long as you multiply R by this, and you could sort of almost see, rise-ish over run-ish, right? Then you get the slope, right? And let's just do, let's just think about this in our head. So let's say R is 1, right? If R is 1, then whatever this proportion is, that will perfectly give us B1, right? Also, if R is 1 and these two have a very similar standard deviation, so the spread of y is very similar to the spread of x, then we should have perfect correlation of 1, right? So in that case, you would be able to sort of see, like, oh, that makes sense. Like, if y is sort of varying in a similar way as x, then yeah, they should have a correlation. They should have a slope of about 1. If y is changing more slowly than x, right? So so for every x, you only go a tiny bit of y, right? So in that case, this number would be smaller than this one, right? And then that would give us less rise, more run, right? So something that looks sort of less slanted, right? Something like this versus a slope of 1, right? So something a little more shallow, right? And that makes sense, less rise, more run. On the other side, if for every y you go very, very little x, right? Then that would look something like this: more rise, less run, right? And so this gives us that perfect relationship between R and B1. All right, now using that information, let's try to solve this problem. Example 1. So here are the 3 pizza companies that we've looked at before: Papa John's, Domino's, and let's say Pizza Hut. And it says find the correlation between grams of fat and cost. And I think these, because I think these are for whole pizzas, and so let's make this $17.50. Let's make this $18 and $20, because it's really cheap to have a $1.75 pizza. And it would be ridiculous to have 100 grams of fat in one slice of pizza. So, all right. So if you look at the examples provided on provided in the download below, we could use this data in order to find a correlation coefficient. So in order to find correlation coefficient, I like to sort of break it down into the component pieces. And the big component pieces I'm going to need are the z-score for x and the z-score for y, right? And I'll say the z-score for fat and the z-score for cost. So z-score for fat and z-score for cost. In order to find the z-score, I would need to put in the difference between this and the average, right? One thing that might be easier is if we actually just create a column for averages, because we're probably going to need this again and again. So why don't we go ahead and get those averages? So I'm just getting the average cost as well as average grams of fat. And I'm just going to color it in a different color so that we know that this is an entirely different thing here. All right, now that we have that, now it'll be easier for us to find the z-score for fat. So here we want to get x, our fat, minus the average. And we probably want to lock that in place. Oops. And we want to divide that by standard deviation. And the nice thing about Excel is that it already has a function for standard deviation. And this one will give us the n-1 version, right? So I can just take this data. Oh. Keep overshooting. And I want to lock that data down. I don't want that to move. Right? Actually, I probably want to copy it over to E later, so I'm just going to unlock the B part. As long as I stay in the same column, as long as I stay in column D, it'll use column B. But if I move over to column E, it should use column C, right? So let's try that. So here we see that z-score is -1, that's 0, and 1. And that makes sense. Your z-scores totaled together should roughly equal 0 because you're getting how many distance away on the positive side, how many distance away on the negative side, and they should balance out if you really have the mean. And so let's check this formula. Yep, it's using B3, but it has the average, and it's getting that standard deviation. Perfect. All right. So once I have that, I could actually just copy and paste this over here. And here we see, now it's using C and this average and getting the standard deviation of this data. Perfect. And we see roughly, you know, the negative side adds up to the positive side. Okay. So now that we have these individual z-scores, now we need to get the z-scores for fat multiplied by the z-score for cost. And that's real easy. This times this. For every single data point or case that we have, and we have 3 cases here, the 3 different brands of pizza, right? Once we have that, instead of the average, well, actually we could just get the average all at once because we could just put it all in one formula, right? We could just sum these together. Could sum those together. And we want to divide by n-1. In this case, it's 2, right? If you wanted to put in a formula, you could put in count minus 1. But I'm just going to put, for our purposes, 2 here. Okay. And here we get a very, very high correlation where it's very, very close to 1. As cost goes up, z-score goes, as cost goes up, fat goes up, right? As cost goes down, fat goes down, right? And so they have a very positive correlation, and it's very liney. It adheres very closely to the line, right? and so here we could see that that this data is very, very highly correlated. It has a strong correlation. We don't have a lot of points, but apparently they fall very, very close to the line.